Hey guys, welcome to another video. Today's learning objective is to recognize, sketch, and interpret graphs of linear functions, quadratic functions, simple cubic functions, the reciprocal function of it's probably a typo, of y equals 1 over x with x does not equal 0, and for higher level exponential functions and some trigonometric functions. Okay, so it's a bit of a longer video, and kind of as usual, there's not going to be that many worked examples in this, in the sense that it's kind of a very much a theory-based lesson. I'm just going to talk you through kind of what the graphs look like and the theory behind it, and the questions I'll ask them at the end. So the prerequisite knowledge on this is kind of remembering what functions are. Remember kind of inputs and outputs, that kind of language I talked about, and how they can be turned into graphs like the one here. But yeah, let's get into it. I'll walk through each of these graphs and kind of show why they might look like this and how you might sketch them, for example. So linear functions. This is something we've seen kind of a lot before. Linear functions are just straight lines, if we remember that. So kind of these are kind of the easiest to recognize. Can you see a straight line? You know it's a linear function. To sketch and to interpret. To interpret really means that if you see like a straight line like this, you'd be able to say like the equation of the line is this. So that's kind of what it is. And remember, if you weren't to find the equation of a straight line, it comes in the form of y equals mx plus c, and then m is the gradient. So we remember how to calculate the gradient, which is change in y over change in x. Remember, rise over run, and the c is the y-intercept, if you remember that as well. So if you remember those two things, you can kind of you can look at a graph and say, oh, the y-intercept is over here. Sorry, yeah, the y-intercept is over here. The gradient is kind of, we can look at the rise here divided by the run here, for example, and then kind of get the equation right, and you've interpreted it. To sketch it is again a bit easier because you can just plot two values. Say you can plot this value and this value. Take a ruler and just draw a straight line through it, and there you've sketched it. And again, obviously a lot easier to recognize as well. You see in a straight line. Let's talk about quadratic functions. We've seen a few of these before. And let me zoom in real quick. So remember we've talked a lot about kind of positive quadratics in the form of kind of ax squared plus bx plus c, and then if a is positive, it's a positive quadratic like this. So that means kind of a happy face or a smiley face. So remember, this is called a parabola, and then the positive quadratic has kind of this happy. It's called a positive parabola, but I remember it's kind of a happy smiley face. And if it's a negative quadratic, i.e. a is less than 0, or a is kind of a negative number, then you have kind of this sad face or a negative parabola. And if you wanted to kind of interpret this and find the equation, well, remember the kind of if you remember, the fact is how we find the roots of the equation. So remember, if we wanted to find the roots of the quadratic, what we do is we kind of have our quadratic, or whatever it is. Say it was, I don't know, y equals x squared plus 4x plus 3. When we find the roots, right, we have x. When we factorize this, remember the roots are at kind of x minus 3 and minus 1, because that's the way this becomes 0. So remember how when we solve the equation, what we do is, if you wanted to go from kind of looking at the graph, what we can do is we can find the roots. You can say the roots, or say if the roots were, for example, I don't know, if we look at the graph and the roots are, say, 0 and 1. Well, we know kind of one of the brackets is going to be x minus 0, and the other bracket is going to be x minus 1. And you say y equals that. And then what you check is that kind of this when you multiply it out, you check that you get in this case, you get, let's just say I'm saying x to x minus 1. If you multiply this out, it comes to x squared minus x, right? And then you can check, for example, in this case, the y-intercept, because there's no constant term, the y-intercept is 0, right? So you check that. Or if you kind of want to look at a more kind of a bit of a harder example, let's look at this graph here. So I've just plotted this. They might give it to you, for example. You might have to sketch it, for example. So if we zoom in, we can see that the roots are at minus 1 and at minus 3. So we go back to this page, we'll have it in the form of y equals, you leave an a in the front here right now. You go x, it was x minus 3, and then x minus 1. And now you have kind of, a x plus 3, x plus 1. And now when you multiply all of this out, right, you'll get kind of a into, you know, some x squared term, some x term, plus a 3 at the end, right? And that means your y-intercept is kind of, if a was 1, your y-intercept would be 3, right? But you look at kind of the graph, you say, okay, here in this case, the y-intercept is 0, 9. So kind of 3a, so when you can say kind of x equals 0, y equals 9. And if we look at this above, when kind of, if we do multiply this out, it becomes x squared plus 4x plus 3, right? And then we do x equals 0, then y in this case is 3a. So 9 is equal to 3a, and a is equal to 3. And then, therefore, you know, the quadratic is what? 3 into x plus 3, x plus 1. You know, this is a lot harder of a question to ask, for them to give you a graph of a quadratic and then turn that into an equation. But remember, there's two steps to it. Remember, just first thing we do is find the roots, and we plug it into the form of x minus root 1. So let's say x minus a, and then x minus b. These are the two roots. And then you stick a kind of a term out here, you know, whatever you can call it, k for example. I've already used the a here. And you just check that when you multiply this number by this number, and then by k, these three numbers together, you should get the y-intercept. But again, that's kind of a lot harder to do. Like, they're less likely to ask a question like that. But what is important to remember is you can recognize this parabola shape, meaning a quadratic, and you can remember the fact that positive quadratic is kind of looking like this. It's happy face, and negative quadratic looks like this. That's a kind of key piece to remember. And if you also say sketch a quadratic, if you also sketch a quadratic like, I don't know, y equals x squared plus 12x plus 9, for example, you can do that just by kind of plotting some points and then putting a curve through it. The points you need to care about is finding the is to factorize this and finding the roots and the y-intercept. And once you've done that, you can do that. I think I've talked about plotting quadratics and stuff in a previous video, so just check that out. And if you're ever confused, just plug in some numbers, and they'll give you a graph paper, and in that you only have to consider the quadratic within that range. And when you do that, you only have to plug in a few numbers, and you can kind of see what quadratic might look like. Let's move on to a cubic. This is what a cubic kind of looks like. They're not really going to ask you to find the equation of this cubic. That'd be quite a mean thing to do. But yeah, just look. This is what a cubic looks like. You just need to be able to recognize this. This is a positive cubic. I've actually got some plotted over here. So if we go over to cubic, so this is a cubic y equals x cubed. It looks like this. So you should notice actually it's it's flat over here. That's the kind of special part about it. A negative cubic is the same thing as a positive cubic, but kind of flipped around, if you can see that. The red is a negative cubic. And now if we kind of add like a random cubic, it looks like a bit like this. That's a negative cubic now. You kind of have this distinct shape of the going up and the going down again. And if it's a negative, it kind of flips around. You have this, it goes down and then up, but you have this double, a negative peak, or kind of a down looking peak and an up looking peak. So that's how you can identify a cubic. And to be fair, if you did want to find the equation of a cubic, it's very much the same principle as finding the equation of a quadratic. What you find is the roots or the x-intercepts. You get it into the form of x minus a times by x minus b, then x minus c, and then you times it by a constant out here, and then you just make sure that the y-intercept is equal to the k times by the a, the b, and the c. I'm not going to talk through the logic behind that and why that works, because it's fairly advanced, but just if that does come up, I guess you do know how to do it, but it really shouldn't be coming up too often. So it's just remember the main thing here is to be able to recognize what a cubic looks like. And just if you also sketch one, say this is a positive cubic, a negative cubic looks like, like that. Oh, that's, sorry, plotted wrong. Like that, so kind of, it will kind of go in one direction the whole time, but they're just going to go, it kind of changes the minds here, and changes mind back again to going in the same direction. That's what negative cubic, for example, looks like. And I think, sorry, there's actually and now that's kind of the first view done. There's also something known as a reciprocal graph, and then that looks something like, let me just close this stuff up. So we have a reciprocal graph, so we have something like y equals 1 over x. It looks like this. You've got kind of, it starts off as a really big value when x is really small, so 1 divided by a small number. So, you know, for example, we can talk through this. So if we have the graph of y equals 1 over x, when x is small, right, say x equals 0.1, y equals 1 divided by 0.1, which is 10, or kind of if you have x is equal to 0.01, well, y will equal 1 over 0.01, which is kind of 100. So the smaller the x, the larger the y, and as x tends to 0, y will tend to infinity. So you have kind of y shining off really high, really high, really high. And then as we start to divide by larger and larger numbers, it tends to 0 again. So y divided by, say, so if x is like, say, 1000, y equals 1 over 1000. And then as x gets larger, say it's 1,000,000, a million, then y is 1 over 1,000,000. So as you can see, kind of the larger the x, the smaller the y. So that's why you have something like this. And then on the negative side, you've kind of got the same thing, but kind of if x is minus this, then y is minus that. So that's why it looks something like this. And that's why the y values are negative here. And that's what a reciprocal graph looks like. You'll actually note in the learning objective, if we go back to it, it mentions how x, if we have the equation of y equals 1 over x does not equal 0. And that makes sense, right? Because if you do 1 divided by 0, you don't really get a number. It's kind of a bit weird. Because 1 divided by nothing, that you can see why that poses quite a few problems. So in that case, as I said, as it tends to 0, as x tends to 0, y gets larger and larger and larger, and kind of, if it tends to 0 from the positive side, kind of this way, then it tends to positive infinity, and if it tends to 0 from the negative side, it tends to negative infinity. But to be honest, you don't kind of need to know in depth of why that happened. Just, it's important to be able to recognize that this is a y equals 1 over x graph. And then you can, of course, kind of, if we go to Desmos, we can play around with, the larger the a, kind of the more it moves out, as you can see. So that's kind of another thing to note. But yeah, just kind of being able to see these graphs. Now we move on to some of the higher tier only stuff. These are exponential graphs. So they come in the form of, say, y equals b to the x, and b is just some constant number. So say, y equals 2 to the x. And now let's kind of think through why it looks something like this. I've kind of given the answer away, but it looks something like this, but let's think about why. So good thing to do is if we're ever curious about what a graph looks like, is to consider things like, first thing is just to plot a few numbers and see what happens. So if you do x and y, so when x equals 0, 2 to the 0 is 1. When x equals, say, 2, 2 to the 2 is 4. When x is, say, I don't know, say 10, then y is 2 to the 10, which is a huge number, right? Okay, let's consider somewhere in between then. Let's say when x is 3, y is 2 to the 3, which is 8. X is 4, y is 2 to the 4, which is 16. And then 5 is 2 to the 5, 6 is 2 to the 6, and then that's 64. And you can see for kind of each x we go, right, we're doubling the y value. And then so it gets really large really quickly, as we can see here, kind of this exponential graph. It gets, for every one we go along here, we're doubling the y value. So it kind of goes from 2 to 4, and then to 8, 2 to 4, then to 8, and then 16 is not even on here, right? So 16 will be somewhere up here. So it grows really quickly, and this is called an exponential graph. And if you recognize something like this and you're wondering what kind of the exponential graph is, well, what you can do is, for example, you can look at what kind of x to when x equals, say, 1, what does y equal? So if you know it's an exponential, and if x equals 1, y equals, say, 10, well, you know the graph is y equals 10 to the x. And why do you know that? Because 10 to the 1 is just 10. And so if, say, y is equal to b to the x, and you need to figure out what b is, if you just find out what x equals 1, what the value of y is, then kind of y will equal b in this case. You can kind of see that, right? I can show you an example of Desmos. Again, so you go to exponential, slide of, okay, so if we have something like, if we have one, if you say we had 2 to the x before, you can see how how quickly that grows. So initially when we have 1, it's 2, and then 4, and then kind of 2 to the 4 is all the way up here, 16, and then kind of you can just see how quickly it starts growing. So even by the time we're at 4, we can't even see the next value. So we can have to zoom out, and then you can see how quickly and rapidly it's growing. We can't even see what 2 to the 100 is, for example. We have to zoom out so far. You can the more we zoom out, the more obvious it becomes how quickly it grows. But in most cases, you'll see kind of a zoomed-in version of something like this. So you can, if you can see it growing at a really quickly rate, it's probably exponential. And the way to verify if it's exponential is that, say, you check what 2 to the 1 is, and that's 2, right? Then you see 2 to, then when x equals 2, it should be kind of like not double, but so if you say, if you look at x equals 1, and you find the value of y, say when x equals 1, y is equal to c. Well, in that case, and if you think it's exponential, you'd say it's y is equal to c to the x. And then what you can check is that at x equals 2, if x equals 2 and then y equals c squared, then you've probably got an exponential. So that's kind of a quick way to check. So say when it's b to x to the 3, right? When we look at 1, we have 3. Okay, 2 then should be 3 squared, which is 9. So we go to 2, and there we go, it's 9. So that's kind of the way we can check if it's an exponential graph. And now we can move on to some trigonometric functions. These are a bit more complex, and I'm going to talk through where they come from and kind of why they're important. That's kind of an A-level topic. So, if you do have if you're really curious about this, you can check out the A-level video, which I'll link in the description below. But kind of, this is what we call a sine graph, a sine of x. And it looks like this. And I'm sure you've noticed this here, but it's the x-axis is actually in degrees, not in like 1, 2, 3, 4 as we usually had it in. And that's kind of the fact is because we use sine for stuff like circles and triangles, that kind of stuff. And they'll actually come up kind of later in the video about later in the lessons about where they kind of come from in a brief way. But the A-level stuff, kind of, if you're really curious, you can check it out. It tells you exactly where it comes from. They'll talk about the unit circle, for example. But so sine of x kind of looks like this. It's like a curve here, and it's 0 when x is 0 degrees. Remember, so I'll just write in degrees. Sine of x is 0, and when it's 180 degrees, it's 0, and when it's 360 degrees, it's also 0. But the interesting thing about sine is that it actually kind of continues, and then this pattern actually repeats for every 360 degrees. So when it's 360 here, and kind of it repeats again every 360 degrees. It's what we call kind of a periodic. I'll show you here on Desmos. So we add y is equal to sine of x. If we go down here, look, you can kind of see how it repeats. Just ignore the x-axis here. But you can see how it kind of repeats every, well, it's supposed to be 360 degrees, just ignore what the x-axis is saying here. and you can see how it repeats on kind of the negative side as well. So this is the sine curve, and then the way you can recognize this is that you have this kind of this wavy looking thing. It actually does look like a wave, and then when x is 0, sine of x is also 0. That's the key thing to work out for when sine of x it's a sine curve. And if you actually compare this to another one we have, this is called the cosine curve, and we kind of shorten this to cos, so cos of x. And then in this case, when x is 0, again, you kind of ignore the y-axis in this case. What's really important is to kind of see the general the way it looks more than anything on the y-axis. So when x is 0, kind of the cos of curve is actually like some positive number. It's supposed to be 1. I don't know why the y-axis is kind of messed up here, but it looks like this kind of, again, wave motion. But remember, unlike sine starts at 0, 0. Cos actually starts at 0, 1, and then kind of again it continues as well. I'll show you again on Desmos. Cos of x. Again, it continues, but when it's 0, it's 1. And then again, it carries on in both directions to infinity, actually. And I may as well explain why kind of it repeats every like 360 degrees. And basically, sine comes from this kind of idea of a unit circle, right? And then sine is just basically a kind of, the fact is it's kind of this, if you draw a triangle, and you have a theta here, for example, or sorry, the x here, if the kind of in the circle there's 360 degrees, and the fact is that kind of there's this, I'm not going to talk too much about it, but basically there's a value as x changes, right? As x kind of goes from to here to kind of there, and so forth. You can find a value of sine of x from it, but the fact is, because there's only 360 degrees in a circle, it will just repeat every 360 degrees. So 361 degrees is basically the same thing as 1 degree in the sense of when you have a circle. So that's just something you have to kind of, again, this is a bit more advanced than you need to know, but just remember a sine looks like this and it repeats. And then you've actually got another curve. I know this has been a lot to take in. It's called the tan curve. And the tan curve kind of looks like this. I'm not going to again talk about where it comes from. That's a bit more complicated. But you kind of just have to look at this and kind of memorize what it looks like. And the tan curve actually repeats every 180 degrees. If you kind of look here, right? If I draw it here. The stuff on the right is basically the same as on the left. It kind of goes up like this, and then something happens, and then starts back down here, and then again that repeats every 180 degrees. And then so again it continues on till infinity. Again, Desmos will prove that. Tan x. So let me close that. Again, you can see how it continues to infinity. Or kind of repeats infinity, rather. So again, what you need to do is just be able to kind of recognize these curves, and then actually on your calculator, you have these trigonometric functions, so you can actually play around with them and see what the value would be. So if you're asked to sketch it, right, and you forget, for example, the difference between sine of x, what the sine curve looks like and the cos curve looks like, just check on your calculator what sine of 0 is, and you see sine of 0 is 0, so it starts at 0, 0, and then you remember it's a wave, and kind of you can draw that, and then you can just check these values, so they, like 180, 360, 90. So just check values in kind of multiples of 90. So kind of, if you're asked to plot, say the question is sketch a sine curve, and you've completely forgotten what it looks like. Besides the fact you remember it looks like a wave, right? What you do is you say, okay, x sine x. So you check x when x is 9, so you check 0, 90, 180, 270, and 360. Those are kind of the, 5 key values that you need to check, multiples of 90. And then you can, 0, 1, 0, 1, 0. and that's what it comes out to. And you remember, okay, you can plot that like this, and 90 is 1, 180, sorry, minus 1 here, 180, 270, so yeah, minus 1, and then 360, right? And then you remember it's kind of a wave-looking thing. You go, oh, wave, and then there you go. And if it was cos, you'd have a similar procedure, except for the fact it would start up like this. That's very badly drawn, sorry. Oh, God. So it would look like something like that if you had cos instead. So you'd go through that same procedure. Just remember, if you're ever confused, remember sine and cos looks like a wave, and you check multiples of 90. The same thing you can do with tan, but remember, tan kind of, it does what it wants basically, and it goes off to infinity at one, kind of like that, and then it starts again at negative infinity. So if you put in values of tan of 90, you're not actually going to get value. So what best to do is say tan of 0 and then tan of like 89, for example, which will give you a really big number, and then tan of 91, you can remember kind of it starts off really, really negative, and then here it's really, really positive, and then just kind of remember tan is like that. So in these cases, like it's something new. You kind of have to memorize what they look like, and if they come up, then you can interpret them. But that's the key thing here. So I know there was kind of a lot covered in this video. A few different functions that I've talked about. Some a bit more basic, like linear and quadratic ones, and then new ones like cubic, reciprocals, exponentials, and these trigonometric ones. And what's key here is kind of is looking at them and remembering them. And the best way I find to remember them, if you ever forget, is to kind of plot a few values, see what happened, try to remember it. It's somewhere in your brain, you can kind of remember what the general shape looks like. And one good thing to do is if you go in Desmos and actually just play around with them, and say, you can, if you put in, say, if you go to say, cubic function, or say even, say quadratic function, you can put like ax squared, and you add these sliders, and you can kind of play around with this, and then see what kind of different quadratics look like if you change the values. So it's quite useful to try this out. But yeah, I hope that all made sense, and I'll see you guys in the next video.